Welcome to the first episode in a series where I make a solar power control system for my house. My original reason for wanting to add a solar power system to my house was primarily to learn more about solar, but I also thought it would be nice to have as an emergency power source. Well, I live in Japan after all. I guess I also had a general expectation that the system could at least pay for itself in the long term as well, but the financial aspect really wasn't that important. In truth, I was planning to do this series at a much later date actually, after I sorted out all the CNC and PCB stuff that I've been working on lately. Well, lately as in a few months ago. But it ended up that I needed to build this solar controller now in order to get my solar system up and working. And you can probably tell by the lack of videos lately that it takes quite a bit of time to complete these projects. Unsurprisingly, it's not just magic after all. And some of you might be disappointed to hear that there is no PCB making in this first solar project. Instead, I rely mainly on plug-in modules wired by hand to a prototype board. I was simply just not confident that I would get the design right first time, especially given my lack of experience with solar. I thought it'd be better to get something online quickly and be able to work quickly to make changes as I learn about how things work in the real world. But don't despair, undoubtedly a PCB for this will be made at some point in the future. Now this project was actually pretty frustrating at times, but the outcome was super satisfying, so with any luck you will find it interesting too. Anyway, let's start off with a little background. The story actually started about 5 years or so back when I installed 3 255 watt solar panels on the roof of my house that I was building at the time. Now 3 panels don't seem like a lot, but this was pretty much all I could easily fit in the available space. But even so, my hope was that I could eventually run all of my house's lights and ventilation fans using the power generated by these 3 panels. Now historically it would have been impossible with old incandescent light bulb tech, but with LED light fixtures throughout, I thought it should not be too much of a stretch to make it work. And it's sort of a nice goal to have, because instead of saying I generated a tiny fraction of the power that I use each day, I could instead say I replaced reliance on grid power for an entire critical function in my house. And that sounds much more satisfying, doesn't it? During the construction of the house, I actually used this system for the site power, driving a small fridge, some lights, and all of my power tools, most of them rechargeable. And for that system I used a very cheap PWM solar controller, a couple of cheap Chinese inverters, and a bunch of lead-acid batteries. Overall, the system was a real lifesaver, providing a pretty much persistent source of power throughout the construction, and allowed me to use the gasoline generator much less, only when I absolutely needed to. As the construction proceeded, I also prepared a few parts that I would use in the final installation, such as a proper MPPT solar controller and a automatic mains changeover box. I also had my electrician prepare the house's circuits for the lighting and ventilation so that they could easily be switched to my solar power system at a future date. Sadly, and as you would expect, by the end of the construction I was pretty much out of steam. I was also faced with needing to replace all the lead-acid batteries. The original batteries would now barely hold a charge after 3 years of constant use. And actually, I think the battery problem was a key thing that halted my overall enthusiasm for this project at the time. I really didn't want to be replacing lead-acid batteries every 3 years. While not expensive, it's a real hassle to dispose of the old batteries, and these things are bloody heavy, enough to do your back in when pulling them in and out of where they've got to go. I also didn't want to use lithium-ion batteries either, be it flat-pack batteries, which are a huge fire hazard, or cylindrical cells, which are not much better in that regard either. And as you need a ton of those, you're probably increasing the odds that you're going to have some sort of failure at some point in time. I mean, how many times have I seen a pack of 4 or 10 cylindrical lithium-ion cells with a single dead cell taking down the entire pack? Well, actually more times than I would actually like to think about. So taking all that into account, and given that any return on any additional investment would be marginal at best, my motivation for the project pretty much went cold. And basically, for the past couple of years, the solar panels on the roof have pretty much been sitting there and doing nothing. But then recently, a couple of things conspired to motivate me to take another look at this little project. The first thing is lithium iron phosphate batteries, otherwise known as LiFePO4 batteries. Probably not saying that right, but I don't really care. Anyway, LiFePO4 battery tech had finally matured to the point that it was now mainstream, making it both reliable and reasonably priced. And for my solar application, LiFePO4 batteries should be able to last for at least 10 years, as most of them are rated for about 4,000 cycles, even when using them at a 80% depth of discharge. LiFePO4 batteries are also relatively light, making them easier to handle, and would use far less space compared to lead-acid batteries. In my case, this means going from 4 pretty huge and heavy lead-acid batteries down to 2 smallish LiFePO4 batteries, and that still achieves pretty much the same usable capacity. On top of this, LiFePO4 batteries are nowhere near as hazardous as the lithium-ion options. Not fireproof, of course, but still far superior. However, it's not all roses, as one would expect. LiFePro4 batteries also do have their problems too. An interesting one is that if you charge them when they're too cold, you will definitely kill them. And charging or discharging them beyond the specified range is probably also flirting with disaster. Thankfully, there are heaps of LiFePro4 batteries out there now with built-in battery management systems, or BMSs, and these pretty much will save us from our own stupidity. So as long as you choose a relatively mainstream brand of LiFePro4 battery with a built-in BMS, as far as I can tell, it will be pretty much a stress-free experience to use them. So now we finally get to the second thing that pushed me to revisit this project. And that's something most people around the world have been experiencing recently. And that is crazy high electricity bills during the middle of 2022. And I think we can all thank Putin for that. So for my case, that meant seeing bills that were twice what they typically are during what is already a pretty expensive winter heating season. And naturally something with that degree of deviation from the norm is going to catch your eye. Now the financial side of things was never a primary driver for this project, as I said before. But even so, the payback for any additional investment into solar system is going to be much, much quicker when seeing crazy electricity prices like this. So that was that. I was finally motivated to try and finish the solar project, which I'd actually started 5 years before. So I went ahead and bought two Dr. Prepare 12 volt 100 amp batteries on sale from Amazon. I think the pair cost around about 600 USD, and the price is pretty damn cheap for 2400 watt hours of usable capacity. Around the same time, I also did some testing of my old 2000 watt inverter, and that sort of indicated that it seemed to be a little bit unwell. And honestly, when using it with power tools during the construction phase, it had always behaved a little bit weirdly, with a very slow ramp up, which often caused my table saw to take around 15 seconds to spin up fully. So I bit the bullet here too and spent a whole $200 on a brand new cheap 2000 watt inverter. Felt a bit like replacing bad with bad really, but I at least hoped that such a device would have seen some improvements over the past 5 years, following the general trend of Chinese made stuff. On arrival, however, it looked pretty much the same as the cheap Chinese inverters of the past, but in testing at least, the general behaviour seemed a little bit smarter, and it even has a nice little status panel too. And looking at other people's YouTube test videos for this specific inverter, it seemed to deliver the rated capacity with no problems, and it didn't seem to have any of that slow ramp up issues. But I haven't tested it with my own table saw yet either, so I can't be entirely sure. When I use the scope to look at the output, however, it's a little bit off frequency by a few percent, and surprisingly a bit worse than my older inverters in this regard. It also has some huge nasty switching noise spikes on the output, but so do the older inverters too, so I guess it's much of the same in that respect. Actually, I discovered this type of noise seems to really upset some models of remote controlled LED light fixtures, sometimes causing them to flicker constantly. I expect the internal microcontrollers are probably suffering an upset from all those nasty spikes. Thankfully, I had two huge ferrite beads on hand, salvaged from some old equipment I scrapped at some point in time in the past, and adding them to the AC output line completely solved the problem, which was a big relief. So overall, pretty good I guess, but I don't have any delusions that this new cheap inverter is going to last 10 years or so either, but I guess we'll just have to wait and see. So that's the basics of the system, the 3 old solar panels which I'm going to reuse, the new MPPT controller which I bought a few years back, new LiFePro4 batteries, new inverter, and the new automatic changeover box, which I also bought a few years back. All seems pretty simple, right? Now let's take a look at how I connected everything up. For the system I used during the construction, I simply wired everything together using the terminals on the back of the inverters. And that worked fine enough, but the cable management is a bit of a mess, and it's quite difficult and dangerous to swap out components when you need to do that. Over the past couple of years, I've actually been scribbling some designs about how I was going to put this all together, trying to come up with some common connector and bus box design. So I at least had some basic concepts in place, but the final design was far from locked down. But the basic idea was to have a box or a panel with a bunch of Anderson connectors where I could easily connect or disconnect components when I was working on them. Now relying on the Anderson connectors alone for quick connect and disconnect is simply not practical, especially with those big 175 amp connectors, which are a real struggle to connect and disconnect. So the box would also need to include some isolation switches, one for each of the connectors, and that would allow for quick connect and disconnect of any of the devices. I also wanted to add a shunt to each of these circuits to allow for current monitoring. And finally, there had to be some space in the box so I could, in the future, add a microcontroller board for monitoring and data logging things such as voltage and current. So this is the final design I settled on. It has connectors for 5 devices, 2 50 amp ones for charging sources, 2 175 amp ones for batteries, and 1 175 amp one for the inverter output. The positive rail for each connector passes through the isolation switch, then through the shunt before connecting to the positive bus bar, which is located on the other side of the panel. The negative rail is connected as directly as possible to the negative bus bar, which is also located on the other side of the panel. And doing that way means that on the back of the panel here, we have a good amount of distance between the positive and negative bus bars. This, combined with the fact that the back of the panel is also fully enclosed with a perspex cover, should keep things pretty safe. Now, the front side of the panel also gets a perspex cover, but it's not fully enclosed like the back. There are a few gaps here and there. Even so, only the positive rail is exposed on the front side of the panel. You can also see here, next to the breaker, I have 3D printed some covers for where the positive and negative rails first connect into the panel. And that's really the only point where the negative rail could have actually been exposed on the front side of the panel in any case. So on a different note, but another interesting part of this puzzle is the mains automatic change-up unit, or ACO. This simply looks at the DC bus voltage, and when the voltage exceeds that configured value, it will switch to using the power from the inverter. And following that, once the battery discharges and the voltage drops below another configured value, it will then switch back to using the grid power. The supply power for the ACO, which also serves as a sense voltage, is simply connected by wires to the bus bars with a 1 amp fuse in series for safety. And there you have it. That's the entire design. So I stuck everything under the floor where it would live, connected everything up, switched it on, and hoped for the best. Actually, after switch on, everything appeared to be working pretty well. Solar panels charged the batteries, the ACO switched on to take the power from the inverter, and it all looked pretty promising. Well, that was, however, until I checked the system the next morning. This is when I found that the solar controller was showing the good old battery frown face symbol, indicating a bad battery. Definitely not something you want to wake up to. Thankfully, however, the ACO did its job well and had switched back to the grid power, so at least something was working as expected. Now to solving the problem. After checking, I found that one of the battery's BMSs had actually stopped the battery from outputting any voltage. And as these batteries are connected in series in a 24 volt configuration, this resulted in zero voltage being presented to the DC bus. To attempt to recover this, I connected my lab power supply directly to the offending, or possibly offended, battery and let it charge for a while. And sure enough, it did come back to life. Quite a relief, actually. So clearly, over-discharging the battery was the root cause of the failure, but as the failure mode is difficult to recover from, it's definitely something I needed to avoid. Actually, I was already worried about the over-discharge risk, but I didn't expect the BMS to actually disconnect the battery completely. But in hindsight, of course that makes sense. I was actually thinking that once the battery voltage dropped low and the ACO switched the load away from the inverter would likely happily idle there until the sun came up the next day. And in the worst case, where the voltage dropped too low for the inverter to be able to operate, I expected the inverter would go into a fault-type state, stop drawing any notable current, and then naturally the inverter would have self-recovered once the voltage recovered to a reasonable level. Unfortunately, however, this is where my assumption was totally wrong. After doing some tests with the new inverter on the bench, I actually discovered that new inverter would keep operating all the way down to 19.8 volts. That's impressively low, but that's actually a huge problem. And that's because the LiFePO4 battery's BMS is actually disconnected around about 10 volts, or 20 volts with two batteries in series. Throw in a bit of natural imbalance between the two batteries in series, and the situation probably is even worse. So with my fabulous system design, each day after the normal discharge cycle completes, the battery's BMS is now basically guaranteed to kick the battery offline, since the inverter will just keep operating well beyond the limits of the shutdown point of the batteries themselves. And the ultimate icing on this cake is that there's simply no way the system can self-recover itself once in state. You're basically just stuck looking at the frown face on the solar controller. So this is a big problem. I just spent $800, did a heap of work building the connector box, wiring everything up, etc., and basically it's a big failure right out of the gate, and with no easy fix in sight. Now, I possibly could change the ACO cutoff settings to be much higher, and that would leave more capacity for the inverter to idle longer before it was causing any problems, but this seems crazy because you would need to sacrifice a big chunk of the battery's capacity for basically nothing. And even doing that doesn't even entirely provide a guarantee that the same problem won't happen again, as the underlying problem is still there. Bench testing of that inverter showed that it needs around about 15 watts just to idle. So that means that you probably would want maybe at least 1 day of idle capacity to make sure that you can avoid that scenario. And that's like 360 watts, or 15% of the effective battery capacity. It's also hard to line up the exact remaining capacity based on the voltage alone. So it's going to need a heap of experimentation to make that work. And who knows if this setting is going to remain stable as the battery ages. In any case, I just didn't like this as a solution. Instead, we need to find a way to turn the inverter off when it's not in use and simply get rid of that unwanted idling load. And just a little caveat here, just in case someone in the comments wants to point it out, A lot of these Chinese solar controllers actually have an internal switch to enable or disable a load directly, usually indicated by a little light bulb symbol on the device. Actually, even the cheap little PWM1 that I'd used before had that feature. But after a little research, the common consensus out there in the internet land seems to be that using this feature should be absolutely avoided. Apparently they're not designed to cope with any serious loads, and if you kill your solar controller, you're really going to end up in a world of hurt. It's a shame, however, and a little bit frustrating really, because I think the EP1 controller I am using appears to have some intelligent automatic controllability of this output, and possibly could have been a quick fix to the problem that I was dealing with. So anyway, the only remaining option is to build something myself, something that will automatically switch the inverter on and off when it is and isn't in use. And ultimately, I decided if I was going to make some microcontroller project to solve this specific problem, I might as well make the whole solar power monitoring system that I'd always planned to make, and simply include the inverter control as a part of that solution. So yep, what was a relatively small project turned into a huge project in the end. Anyway, I'll break this project up into a couple of episodes, because if I make one huge video, most people won't watch it. That's evident by the statistics. And as you can tell, this is basically the intro video. So let's at least take a quick look at the design overview for the controller. For the microcontroller, I decided to go with an ESP32, specifically because it has Wi-Fi, which allows me to set up a website to remotely monitor and control the thing. All this stuff is located under the floor, so remote control ends up being a pretty important component of this project. And this is the first time for me to use an ESP32, so it's definitely going to be interesting to see what I can do with that. The new inverter I bought conveniently came with a remote control panel, so my idea is to try and reverse engineer that and figure out a way to switch the inverter on and off using the ESP32. I also want to measure the current in each of the shunts. The method would be much the same as I did with the mini lathe, using a current sense amplifier IC to create a voltage that I then read with an ADC. Sadly, and according to all accounts out there, the built-in ADC in the ESP32 totally sucks, and is not to be used for any applications that require even a basic degree of precision. So instead, I will use an external ADC for that, specifically a ADS1115. And as you can imagine, having to get measurements from 5 individual shunts is going to increase the complexity somewhat, and that means I'm going to need to use 2 of those ADC modules. Actually, when I did my original scribbles for this design a couple of years back, I was thinking of using a dedicated AT-Tiny85 for each of the current sensing circuits, with the idea of these acting as co-processors to take some of the load off the main microcontroller. But for now, I've pretty much given up on that idea, and instead I've decided to see how hard we can push the ESP32 and try to do everything in that one microcontroller. I'm also adding an external real-time clock, the venerable DS1307 module. Now, of course, if I tried hard enough, I possibly could do a clock using the internal ESP32 timers, but that all just seems like too much hard work to figure it out. And with the built-in battery backup on the DS1307 module, well, it's pretty much a no-brainer to use that. And as this controller and the entire solar system is located in the same small cavity under the floor, I'm a little bit worried about temperature buildup, especially in summer. So of course I'll be adding a DS18B20 to monitor the ambient temperature. I also added 16 megabytes of SPI flash memory for short and long-term data logging, with the ultimate goal of making some nice graphs showing performance over time. Now I doubt I'll make much progress with that during this first implementation, so basically I'm just putting it in place now so that I can easily add that feature at a future date. And for the final, and rather large elephant in the room, is how do I power this damn thing? Now as I want this system to be able to operate in a fully standalone configuration, I'm going to power the system directly from the LiFePO4 batteries. And I want to do it that way to cover the emergency case where the grid power is no longer available. Obviously I want to be able to keep the system running. So that firstly means I need to extract the stable 5 volt supply rail from that 20 to 30 volts that the LiFePO4 batteries will supply. And as I've experienced situations where the LiFePO4 batteries BMS can actually disconnect the power altogether from the DC bus, I'm going to add some localized battery backup to make sure the controller can still run for extended periods of time, say at least 24 hours, even after the external supply volts are lost. Actually, for various reasons, this power supply system ended up being pretty complex. But even so, it's a very interesting part of the project. So in the next episode, I will go over that in some detail to show how it all works. Sounds exciting, doesn't it? So that's it for now. I guess I'll see you in the next episode. See you then.